Okay, hi everyone. Welcome back to section 7.2. And in this video, we're going to take a look at some basic examples of finding an inverse of a Laplace transform. So remember the inverse of a Laplace transform. We were given a Laplace transform function, and we're trying to find the inverse of this function that turns it back into a regular function. Okay, so in order to do these inverse Laplace transforms, it's definitely handy to have a table somewhere near you so that you can identify what these Laplace transforms would turn back into. Okay, so here's a table of some basic Laplace transforms that we've been dealing with so far. We're going to utilize this to find some inverse Laplace transforms. So let's go ahead and look at example one. So I have the inverse Laplace transform of 1 over s to the fifth. Okay, so I want to see what 1 over s to the fifth might look like. Okay, so if I go to my table off to the side here, what does that look like to me? Like 1 over s to the fifth. Well, to me, that looks like this setup right here. I have some s to some power. Okay, so I have 1 over s to the fifth, because we're given 1 over s to the fifth. And so that's what this looks like most to me out of all of these here and what we've learned so far. So to me, I'll make a note here, you know, to me, it looks like t to the n equals n factorial over s to the n plus 1. Okay, so um, let's see, let's kind of identify what 1 over s to the fifth is. Like, that n to the n plus 1, this is like uh, n plus 1 equals 5. So that must mean like, 4 plus 1 equals, or maybe I'll write it like this, like that just means like n equals 4. Okay, so that's where we're getting this from. Okay, but if that's the case, then I'm going to need an n factorial on top. So I'll make a note here, like there is a n factorial on top. Okay, so what might help us figure out this exact Laplace transform is sort of write it like that. Inverse Laplace transform. There should be a 4 factorial on top, s to the fifth. Okay, so that's what this should look like, but we just have a 1 here. So in order to just to account for there just being a 1 there, what I need to do is multiply this by 1 over 4 factorial. Because ideally, you know, that would account for there just being a 1 there. Okay, but this is ideally what this Laplace would look like. And so the Laplace of inverse Laplace of 4 factorial over s to the fifth, well, that would just be t to the fourth. Because what is n? N is just 4. Okay, so that's what the Laplace inverse Laplace transform would be. But we do need to consider the 1 over 4 factorial, and that's t to the fourth. So we could, clean this up a bit, maybe put t to the fourth over 4 factorial. And, if you're curious about what 4 factorial is, it's like 4 times 3 times 2 times 1. So 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So, you could say t to the fourth over 24, but either or of these are correct. You could leave it 4 factorial, it is not a big deal. Okay, so one thing with these inverse Laplace transforms that's really nice is that you can actually check to see if like this worked out well. So How can we check? It's just find the Laplace transform of what you found. So we can just find the regular Laplace of t to the fourth over 4 factorial. I'm going to use our original answer before we factorialed. But yeah, like what we could do is maybe bring out that 1 over 4 factorial. Just have t to the fourth. But then, what is the Laplace of t to the fourth, right? T to the fourth would be 4 factorial over s to the 4 plus 1, which is 4 factorial over s to the fifth, which is what we kind of broke this down to, right? So if we come back here, 1 over 4 factorial times 4 factorial over s to the fifth. Well, how about that? The 4 factorials cancel out, and I'm left with 1 over s to the fifth matches. Okay, so that is the idea behind the inverse Laplace transform. You're trying to match it up and see if you have to deal with any different types of constants, factorials. Okay, so that's the idea. So let's go ahead and try the next one. So maybe I'll say like answer is there. Um, so like I said, let's go ahead and try out the next one. We have the inverse Laplace transform of 1 over s squared plus 7. Okay, so 1 over s squared plus 7, what might that look like to me? So let's go to our table. Let's try to use our table. I'm going to erase this. Okay. And so, um, 1 over s squared plus 7. So to me, that looks like sine right here because we have a constant on top. Because what are we comparing it to? 1 over s squared plus 7. We have a constant on top. A is a constant. It wouldn't be cosine because cosine has an s on top. Okay, so what this criteria is fitting into is sine. Okay, so we're going to use sine. That was what it looks like to me. And we're going to try to manipulate this into a Laplace, inverse Laplace transform. So, I can make a note, uh, looks like sine of AT to me because constant, oops, constant up top. I'm talking about this just regular constant 1 up top. Okay, and then just to have handy with us, sine of AT, the Laplace transform of that is a squared over s squared plus a squared. Or not a squared up top, it's just regular a. And so I'm getting that from here. Okay, so let's go ahead and try the inverse Laplace this. We need to manipulate it like we did before. So what can I identify here? So um, we have an a up top and we have an a squared on the bottom. So one thing I see here is like s squared plus 7. This is supposed to be like 7 is supposed to be a squared. So what I could see from here is that this is like s squared plus square root of 7 squared. Okay, square root of 7 squared equals 7. So in this situation, a equals square root of 7. Okay, so if that's the case, there should be a square root of 7 on top. So what I could do is rewrite this inverse Laplace transform as square root of 7 over s squared plus square root of 7 squared. But there's this 1 up top that I need to account for. So what I would do is multiply this by 1 over square root of 7. Because yeah, these would cancel out and I'm left with 1. But we're trying to inverse Laplace transform this, so we need to manipulate it a little bit to make the transformation easier to see. But yeah, like what is the inverse Laplace? Excuse me, I forgot the inverse symbol of square root of 7 over s squared plus square root of 7 squared. Well, what is a? A is square root of 7, and so our answer would be sine square root of 7t. So what this turns into is 1 over square root of 7 times sine square root 7t. And that's our answer. So we could also check this out. That's the good part about these inverse Laplace transforms is that we can check it. So the way we would check it, like we did before, is find the Laplace transform of 1 over square root of 7 sine square root of t, our answer. So, we could bring out the 1 over root 7 and find the inverse Laplace of sine root 7t. Well, what is that going to be? Let's use our table. Sine of root 7 is going to be, well, using this a over s squared plus a squared, that's going to be root 7 over s squared plus root 7 squared. So that's our check. What we end up with is 1 over root 7 times root 7 over s squared plus root 7 squared. The root 7's cancel out. Square root of root 7 squared is just 7. So I have 1 over s squared plus 7. And checks out to our original question. Okay, let's look at one more example. So we have the inverse Laplace of 2s plus 6 over s squared plus 7. Okay, so this one's a little not too clear from what we're given in our table. So let me erase this. Doesn't really fit any criteria in our table. What I'm looking at is anything here. But what we could do here is actually split up the numerator. So we can split up the numerator. So what this would turn into is inverse Laplace of 2s over s squared plus 4 plus the inverse Laplace of 6 over s squared plus 4. Okay, so now these look a little more familiar to what I could find in my table. And so what I'm specifically looking at are sine and cosine because I have two terms, one with a constant up top, one with an s on top. So it would fit into sine and cosine. So let's come back to the problem and write that down. So, here I'll say looks like cosine of AT because of S on top. And I'm looking at this S right there. It just has a single S on top, so it looks like cosine to me. Because what is cosine? Cosine of AT is S over S squared plus A squared. And our second term, this looks like sine of AT to me because of just the constant on top, just the 6 on top. Okay, so that's why it fits the sine criteria to me. So sine of AT is just a constant A over S squared plus A squared. This we saw that one in previous problem. So the idea is how do I manipulate this to get, A squared, things like that. So one thing I could do for this first term is take out a 2. Okay, so we could take out a 2, like 2 times the inverse Laplace of S over S squared. And what I could do is turn this 4 into 2 squared. So then A just equals 2. What am I doing with A is because like cosine of AT equals, A squared in the denominator. That's why I want to figure out what A is. Okay. Likewise for sine, you know, is S squared plus 4 on the bottom, so I could do the same thing. But that means I need like a 2 on top. So I wouldn't take out the entire 6, but I could make that a 2 on top. So I could just take out a 3. And so what I could have is 3 times the inverse Laplace of 2 over S squared plus 2 squared. And so that way I can know that A equals 2 as well. And just using the regular cosine and sine, what I would have is 2 times cosine of 2t plus 3 times sine of 2t. And that's my answer. Okay, so a couple different examples of inversing a Laplace transform. And the main idea is recognizing your table and the basic transforms that you could use um, to get your inverse Laplace transform. So uh, thank you for watching the video. Hopefully this made sense. Once you practice a few, it'll start to be more clear in the process, okay? But I'll see you in the next video. Take care.